Okay, shall we get going, Karthik?
Sure, sounds good.
Wonderful. I'd like to welcome everyone to another episode of our YugabyteDB Friday Tech Talk series. Thanks, people, for joining. My name is Kannan. I'm one of the co-founders at Yugabyte, and it's my pleasure to welcome Karthik Ramanathan, one of the engineers on the database team, to today's episode. Karthik, would love for you to introduce yourself, maybe tell us a little bit about uh, some of the team or the projects you're working on, and then jump right into the topic.
Sure, sounds good. Thank you so much, Kannan, for having me here today. Hi, everyone. I'm Karthik Ramanathan. I work on the LRT team here at Yugabyte. That's language and relational technologies. And I spend a lot of time optimizing write queries here. These are your inserts, deletes, and updates. So I spend a lot of time in trying to make them more efficient and in trying to get them to run correctly. So today we will be talking about update queries in particular, and specifically about how Yugabyte has tuned update queries in order to run them efficiently in a distributed setting. Great. So I'll introduce the topic of update queries. Today we'll walk through a few basic examples, and then we'll talk about three concrete optimizations that we have done that make the update queries run blazingly fast. And finally, we'll conclude the presentation with a short demo. Right. So before we get to the topic of the optimizations, let's talk briefly about how update queries are implemented in a transactional database. So in databases having multi-version concurrency control, updating a row essentially involves two steps. Deleting the existing copy of the row and then inserting the new copy of the row with modified values. So what's MBCC, you might ask? And at its core, MBCC is essentially a scheme where multiple physical versions or copies of a row are maintained by the database. And this is essentially to ensure that readers don't block writers and vice versa. Right. So let's look at what an update actually looks like in a database. So if I'm updating the row containing milk into oats, what we would end up doing is marking the existing copy of the row for deletion and inserting a new copy of the row containing oats and the updated price. And is that it? Unfortunately, not. So behind the scenes, a lot more bookkeeping operations take place in a database. If you have indexes, those are updated. If there are foreign keys or referential integrity constraints, those are checked for compliance with the modified values. Similarly, if you have unique constraints, those are honored. And several such operations take place really depending on the schema. So how does this translate to a distributed database? So to begin with, the data may be sharded across multiple nodes, and these nodes may be present in different availability zones or maybe even in different regions around the world. And further, if the table has indexes, the data in the table may not really be co-located with the corresponding data in the index. For example, the row containing milk in the products table is present in node 1, but its corresponding index row is present in node 2 here. And given that these nodes may be geo-distributed, network round trips to fetch data back and forth from these nodes could potentially be very expensive. So In summary, I just want to again highlight the different things that we spoke about with respect to updates. So updates are a two-step process. They involve multiple administrative or bookkeeping activities in the background. And a lot of this is made all the more challenging due to data distribution. Right. So let's walk through a couple of simple examples to develop some intuition before we get to the optimizations. So for this example, and for all of the examples that will follow in this talk, we have a table called products, which has an index on the name column. So the name index that you see here is essentially an index on the name column, which essentially contains a pointer back to the main table. And this is the schema that we will use throughout the talk. And in this particular example, we want to increment the price of milk and eggs in the database. So how does the database do this? I'm excluding the two-step process that we talked about for brevity, but the thing that I want you to observe here is that although only one table, that is products, is being updated, the query may have to work with multiple nodes. So here it sees that node 1 contains the row contains milk and node 2 contains eggs, and it updates them. Right. Let's go to a slightly more complex example, which might use the indexes as well. And let's try to update the entry containing sugar to salt. So I'll pause for a second to allow you to think about it. And essentially what happens here is as follows. So the row containing sugar needs to be modified to salt. So this affects both the products table as well as the index. So both need to be written to. The previous example didn't have to do that because there was nothing to update in the index. Just the price was being modified, and as you see, the index column doesn't contain a price. And thirdly, even though it's just a single logical row that is being, or a single entry that's being updated, it may still translate into an operation that spans multiple objects, or rather multiple tables. Here, there's the index table and the main table itself. And furthermore, it may also translate into a multi-node operation. As you see, this involves node 2 and node 3.
Yeah, I think just to put a finer point, or re-emphasize some of the main points. Firstly, just like your products table can get large and needs to be sharded across multiple nodes, and for the products table, the shard dimension is the ID, because you're looking up primarily the products table by its ID, so you've chosen that as the sharding dimension. For the index, on the other hand, if you need to look up this table efficiently by the name, you create a name index. That itself in the system is another table, and that table will have an equal number of entries as the products table. And now that needs to be sharded too. And it's sharded on the name dimension, so there's no natural way to co-shard it. And that's one of the reasons why multiple nodes are involved in the update process, because you not only need to update the name on the products table, but the index also has to be updated to recognize the name change. And in some cases, just changing the name sugar to salt may mean that that index entry actually moves between one node to another. It in this example that Karthik has shown, it just happened to go back to the same node. But if you really had to, it could have very well happened that when you're sharding by the name, maybe salt's position in that shard map ends up being node 1. So more nodes could have been involved. And I think this is all really a setup to point out that while multiple things have to be coordinated as part of the update, on a single node architecture, these things, even if you have an inefficient query or an inefficient query execution model, it's not going to be the end of the world. But in a distributed architecture, it's very important that we design these updates to be as efficient as possible and minimize sort of the number of round trips between nodes and so on. Thanks, Karthik. Please continue.
Absolutely correct. Those are all great points. And yeah, as Kannan pointed out, that it could very well be that in this case, the index containing the entry containing salt hasn't migrated to a different node, but in a different setup, particularly if you have a hash sharded index or a hash sharded table, that could very well end up happening. So let's draw up a blueprint for updating a single row. So we would want to read the row from storage, apply the modifications that the query is asking us to do. We would want to check that the modifications continue to satisfy any constraints that may be placed on the row. Run any associated triggers that are on them, update any indexes that are on them to ensure that they are consistent. And finally, we want to write back the row to storage. And all of this is in really no particular order, but it just goes to show that these are all things that the database may do in updating a single row in its backend. Right. So with that being said, let's talk about a couple of the optimizations that we've done here at Yugabyte. In particular, to talk more about the case that Kannan pointed out about data being placed in different nodes, let's talk about a query which might actually update multiple rows. Here we have a sample query which sets the price to 100 for all of the products that you see on the screen. And let's think about this in terms of the blueprint that we drew up. So this would want to read all the rows that were written, all the rows that need to be updated, and ultimately write them back with the updated price. So intuitively, we might think that the update might look something like this, where we read one row from storage, like so, modify it, and then write it back to storage, and then move to the next node. And but translating that into the illustration that we have here, if we were to read one row and write one row at a time, this very simple query would require you to make 10 network calls or 10 RPCs over the network. And in a geo-distributed database, this is potentially 10 calls around the world. As an improvement, you could try doing something like reading the next row while writing the current row, but that doesn't really make things too much better. You would still need 5 or maybe even 6 RPCs in this case. So,
and just to add, like in case people are wondering, hey, why does an update have to even read the row? It may be obvious, but just to maybe state the obvious. Firstly, databases have to check whether the row that you're trying to update actually exists, right? And some so that in itself, like because you don't want to, if you try say, hey, update row where ID equals 10, we got to read the row to make sure it exists. Otherwise, the update should fail. Another example where you may have to read the row is, in this example, he has price equals 100, but it could have been price equals price plus 100, in which case you need to read the old value of price. So there's different reasons where you need to read the current state of the system and then make the update.
Absolutely. But that's a great point. So,
yeah.
So let's talk about how we optimize such multi-rows queries in Yugabyte. So this query in a very naive implementation might take either 5 or 10 RPCs to complete, and that's really not very efficient. So what we end up doing is we read a batch of rows in one go, and then write out a batch of rows in one go. So we have data that's split across multiple nodes, which we can fetch in parallel, which further saves us time and also cuts how many RPCs or how many batches that we may need. So in this particular case, we have a local proxy which would be tasked with reading all the 5 rows. And since the 5 rows are present across 3 different nodes, this happens in parallel. And what the query layer sees is that it sends one RPC to the proxy, and it receives back all of the 5 rows in return at the end of the RPC.
And in some ways, what we have done is instead of 5 round trip latencies for the read phase and 5 round trip latencies for the write phase, the batching is essentially reducing the number of actual waits. Not only are we batching it, but we're sending it to the different nodes in parallel. So the number of round trips is really one for the early phase and one for the read phase and one for the write phase. Yeah.
Absolutely. Yeah. So as Kannan pointed out, we essentially reduce 5 RPCs for the read to 1 RPC for the read phase, and from 5 RPCs to 1 for the update or the write phase of the query. So this process of reading a batch of rows over a single network RPC and similarly writing it back makes multi-row queries very efficient in a distributed database. And it turns out that this concept is more generally applicable and has many use cases in a distributed database. We, in fact, reuse the same concept with slight modifications for checking things like foreign key violations, for batching nested loop joins, for implementing absurd semantics, and so on. And the underlying concept really is that as long as there's no causal relationship among or between the operations in a batch, you can batch them together. So this is a concept which would allow us to to do both writes to the products table as well as its indexes together, because the writes themselves are independent as the value of the writes has been decided beforehand. And similarly, writes to multiple unrelated tables can also be batched. So we talked about how multiple rows can be updated or read efficiently. Now let's talk about the actual process of updating a row. That is the 2-step process that is involved in MVCC. So as an illustrative example for this, let's create a covering index on the name column in order to include the price as well. So the covering index would so the red line would indicates the key part of the row or the part of the row that uniquely identifies it. So everything to the left of each of the red lines indicates whatever is unique about the row, and anything to the right may or may not be unique. So price is certainly not unique, whereas the ID is certainly unique. So we've created our covering index for the same example above. And now let's try to update the price of milk. So where ID is equal to 101 refers to milk. And let's try to increment the price by 2. So this query contains the 4 ops, or is implemented with the 4 operations that you might have expected. So talking about the products table, we first update the row in the products table by first doing a delete and then an insert, and similarly for the index as well. But here there's a concrete problem here. So the operations 1 and 2 have a dependence on each other. And remember, we said that batching can happen as long as there is no dependence between or amongst the operations. And essentially, the dependence is that we are deleting a row with ID 101 and inserting a row with ID 101. Uh, in order to insert the row with ID 101, the old copy of the row must be deleted first. In other words, if these two operations were interchanged, the delete may well end up canceling out the insert and nothing would get updated. So, and this is because the part of the row that identifies it, or the key, or the portion to the left-hand side of the row isn't really changing after the update. So this means that these operations need to be strictly ordered, and so they need to be sent as part of separate RPCs over the network to the node, and this makes them potentially inefficient. And it's a mirror image for the covering index as well, where the row containing milk needs to first be deleted in order for an updated version of it to be written out.
Yeah, I think just wanted to call out that if the name index had not been a covering index on the price column, you need not this particular update need not have even bothered with the name index. But because the price is included as a column in the index, this is becoming a kind of a update of two parts of the system, right? That is one observation. The second thing you said is like, because the same row is like say in the 101 example, like where the same row is getting updated from milk 5 to milk $7, we can't have both the delete and the insert in the same batch. I think strictly speaking, that's not true. It could have been in the same batch, as long as then within the batch we enforce some ordered apply on the target. But maybe that's what you're going to talk about, like how we handle it and are careful about doing that.
True. That's a great point. Yeah, I'm trying to get to that in the next slide about how we handle this. So essentially what we've done is we have defined a logical operation, a logical update operation, which allows our execution layer to tell the storage layer that, hey, the key part of the row is not being changed. So when you see the update, first delete or mark the row that's identified by the key for deletion, and then paste or insert these updated values as a new copy of the row. And with this semantics, now both of these, we do not need to strictly send them in separate RPCs, or there is no, we have solved the dependence problem. So both of these operations can now go as part of a single RPC. So in essence, we talked about the fact that rows are identified by their key columns. And in a two-step update process, when only non-key columns are being changed, there is a dependency problem that we need to solve, which causes us to need two RPCs. And we got around this by defining a logical update operation, which allows the execution of the query layer to tell the storage layer that the key columns are not being modified. And in order to honor MVCC and all the problems that it solves, the storage layer continues to do the two-step process in the ordered fashion that Kannan mentioned. It's just that we have solved a logical limitation that existed for us prior to that. And again, as Kannan mentioned, this is particularly efficient for covering indexes or indexes that have included columns and for primary key updates. So another thing is that you may wonder why I specifically called out non-key columns in this example, and there are two reasons to that. So if the key column changes, then it gets mapped to a different row, or the identity of the row changes. So there is no strict dependence between the delete and the insert operation. And there is also the possibility, and Kannan referred to this earlier on in the talk, that the row after the update may move to a different shard or to a different node as a result of the update. And so we cannot tell the storage layer in a single node to perform the update, as we would now have to coordinate with two different nodes.
Yeah, we may, it will be like, I think we're about 5 minutes, but we can go a little extra. So let's, move through this.
Sure. So we talked about batching multiple read and write operations and about simplifying the two-step update. But let's talk about cases where we can skip some operations altogether. So to illustrate this, I have a foreign key table. So we're going to have a new table called orders, which has a foreign key reference between product ID, which maps to the ID column in products. This is essentially to say that an order may contain several products, and each product in an order must map to an actual or an existing product. So this is a foreign key reference. And let's go back to the regular index and forget about the covering index. So to illustrate how we can skip operations, and this is the final optimization, let's talk about this query, which says that for a product having a price of $7, set its name and ID to that of milk. So this query may seem quite trivial, but please bear with me. So this is a query that where the optimizer cannot easily remove the redundant columns in the set clause. And this is because the optimizer really has no way of knowing that there is only one column with a price of 7, and that column maps to milk. So, but as a result of an optimizer not being able to optimize this, these columns can incur bookkeeping operations, indexes have to be updated, constraints have to be checked, and so on. And this also updates the key portion of the row, or the portion to the left-hand side of the red line. So this is something that the second optimization cannot solve. And finally, the query may seem a little trivial, but we've seen this pattern several times in ORMs, in prepared statements, which really cannot exclude columns at will. So let's just look at the query one more time, where the price is being set to 5 of a row where the price is 7. So this would involve firstly updating the row in the products table, updating the row in the index. It would trigger foreign key checks on all of the orders that contained milk, because we're updating milk from an old value to milk in a new value. And we need to ensure in the naive or the unoptimized case that there are no foreign key violations here. So the way we optimize this is to essentially remove all of the parts of the query or all of the columns that don't change before or after the update from the query. So to be clear, we don't rewrite the query as such for the reason mentioned previously related to the optimizer. But if we skip performing all of the redundant bookkeeping, all that we have to do is change the price to $5 from $7, and that's exactly what we end up doing. So in essence, we compare the modified value of a column with its existing value, and if all of the columns that an index or a constraint is made up of remain unchanged, we skip performing the operation altogether. And we tend to try to be smart about what columns we do this particular operation for. And just like we talked about the read batching, this concept is also turns out to be pretty versatile. And it not only applies to indexes and constraints, but it finds use in things like before update triggers and in the do update clause in insert on conflict queries or in absurd semantics. Do we have time for a quick demo?
Yeah, I think it'll be good to see what this means in practice, like, right? Like, so, and how can I observe the benefits and things like that? Like, is there, yeah.
Sure, I can do a quick demo of the
Like you explain, analyze or something to show the number of round trips or something. Yeah, that'll be great.
Absolutely, yeah. Okay.
And while Karthik is pulling up that, like in a vanilla Postgres or MySQL, for example, when you do an update to a row, even if none of the indexed columns have actually changed, the indexes still need to be updated, because in a vanilla Postgres, the row always moves around and the pointer to the row from the indexes have to be fixed up. Whereas in Yugabyte, the pointer to the main row is actually a logical pointer, which is the primary key of the row. So as long as the primary key is not changing, an update doesn't need index maintenance if you're not touching indexed columns. So that is a key property that we make use of in doing this optimization, which is super important in a distributed architecture to minimize the number of like network round trips. Right? Yeah.
Absolutely, absolutely. So I'll quickly run through a demo since we're a little over time, but here I have two setups.
You're not yet sharing your screen, yeah.
Is my screen visible?
I can't see it. It's yeah, it's good now.
Okay, perfect.
Yeah.
So I have two setups, both of which are on 2024.2.2, which we recently released. So one of the setups I've tuned to be inefficient to not contain all of the optimizations that I just talked about, and one which contains all of the optimizations that I talked about. And it has the product table from the example with the exact data that we saw in all of the illustrations. Mm-hmm. So let me quickly talk about the run the same examples across both setups. So in the inefficient setup, this was query one, where we set the price to $100 for all of the rows. And this is without the read batching or the write batching. Mm-hmm. And essentially, we see that this query requires 5 round trips to fetch the rows and 4 round trips to write out the rows, because I think some of the writes get combined with the reads. Mm-hmm. And running the same query on the efficient version, we see that there is now a single request to read the rows and a single request to write the rows, which in turn spans all of the 5 rows that are to be written.
Yeah.
Okay. Jumping quickly to the second optimization. Let's create the covering index.
So this time, if the price changes, the index has to be updated. Even if the name is not changing, okay? Because of the covering index property. Are you missing a E? Yeah.
Yep. Yeah.
93 milliseconds and 1 read request and 2 flush requests. Okay.
So the 2 deletes go, the deletes to the main table and the deletes to the index go in one flush. The 2 inserts go in the second flush.
Okay.
And let's quickly run this on the analyze table, and we see that we've shaved off one of the flushes.
Nice.
The timing may not really be representative considering we are updating a single row, and
Yeah, and you might have to run it many times. By the way, do you have a multi-zone setup here or multi-region setup?
it's a multi-zone setup, I believe.
Okay.
And for the final example, let me quickly. Okay, it looks like
Now you're creating just a regular non-covering index, but you're going to bunch of your columns that you're changing haven't. You're providing a bunch of columns in your update, but some of them are not actually changed from the old value.
correct. So if we do a select star from products, I forgot to reset the values, but
That's okay.
let's just say set ID is equal to 101, name is equal to milk, price is equal to oh, sorry, the price is 102, and I
Yeah.
forgot about that. So here we see that a whole bunch of requests get fired off. Again, this doesn't have the read or the write batching,
Yeah.
but if I were to run this real quickly, we see that there is now one read and one write, irrespective of how many constraints or how many things we have to update internally.
Yeah. Could you just do a timing on? Just do a slash timing on one of your windows.
That's what this. Would you like me to do it for the?
Oh yeah, actually, it's already on. Then just say, can you just say select one? I'm just curious.
Sure.
Select one, enter. Yeah, it sounds like your laptop is 77 milliseconds away from the Yugabyte node, and that's why your base numbers are higher. But so I think the timing is a little bit misleading because just like your client is far away from the database nodes. So, but yeah, as you can see from the number of flush requests having gone from like 3 to 1, you can see essentially like if you're not modifying a column, we are automatically able to detect it and avoid index maintenance in many more cases than even traditional databases. And but why it's super important for a distributed database to focus on this level of optimization. So I'm really excited that for our users to when they move to these newer releases of Yugabyte, which have this transparent optimization on. Maybe I think you do have a slide on that, right, Karthik, on when this is coming.
Yeah, I'll quickly conclude with this slide. Uh, there we go. So the good news is that all of these are now GA or generally available. The read batching, we've been doing it for a really long time. The in-place index updates are enabled by default from
You're not
2024.2.
sharing your screen, by the way. Like, yeah.
Yeah, there we go.
Yeah.
And as I mentioned, the in-place updates are enabled by default from 2024.2. This is particularly for the index case, whereas for the table case, we've again had it for a really long time. And the part where we skip the optimization, where we skip index bookkeeping operations, that's live from 2024.2.1. In the example, we saw 2024.2.2, and the optimized case, I did not tune it. It's all what we get out of the box. The unoptimized case, I had to play around with it to make it inefficient. So it's all generally available now.
Fantastic. Yeah. So 2024.2.1 is the release where these things are on by default. Yeah. I'd like to thank, since we're over time, I'd like to thank everybody for joining. See us on another episode of the Yugabyte DB Friday Tech Talk. these upcoming Fridays. We have a lot of content around some of the PG-15 stuff and other topics. So yeah, until next time. And Karthik, over to you for closing remarks.
Thank you, Kannan. It's been an absolute pleasure to work on some of these things and to see it go live. So thank you, everyone, for listening in, and thank you, Kannan, and all the people behind the scenes for making this talk happen. Catch you all soon in a different talk.
All right, bye.